In the silent, fathomless dark between the stars, there are worlds that defy imagination. Worlds of ice, worlds of gas, worlds that drift in eternal solitude. But among the billions of celestial bodies scattered across our galaxy, some are true monsters, born in violence and forever bound to the infernal glare of their parent suns. Imagine a planet forged in such proximity to its star that its years last mere hours. A place where the very ground beneath your feet would not be solid rock, but a churning, incandescent ocean of molten lava. This is a super-Earth. A class of world more massive than our own, yet smaller than the gas giants that patrol the outer reaches of our solar system. It is a realm of extremes, a crucible where the fundamental laws of planetary science are tested. And according to everything we thought we knew, a world like this, so close to the blistering furnace of its star, should be naked. Its atmosphere, any gaseous veil it once possessed, should have been scoured away, blasted into the void by a torrent of relentless radiation and ferocious stellar winds. It ought to be a barren, airless rock, a silent testament to its sun's overwhelming power. But against all logic, against all our established models, this super-Earth is not silent. It is not barren. From across the chasm of dozens of light years, our most powerful instruments have detected something impossible, a whisper in the dark, a chemical fingerprint where none should exist. This super-Earth, a world that should have no atmosphere, somehow, miraculously, does. And the story of how it holds onto this gaseous shroud is rewriting our understanding of what it means to be a planet in a violent and unpredictable cosmos. The notion that we are not alone, that other worlds orbit other suns, is not a modern invention born of high technology and powerful telescopes. It is an ancient dream, a philosophical yearning that has haunted humanity for millennia. In the sun-drenched gardens of ancient Greece, the philosopher Epicurus, gazing at the same night sky we see today, reasoned that an infinite universe must logically contain an infinite number of worlds, some like our own, others profoundly different. He wrote of a cosmos where atomic collisions would inevitably form other Earths, populated by other creatures, living under the light of other stars. It was a breathtaking leap of intuition, a universe of boundless possibility. But for centuries, this idea remained in the realm of philosophy, not science. It was a dangerous idea. In the late 16th century, the Italian friar Giordano Bruno championed this concept of a cosmic plurality, declaring that countless suns existed and countless Earths revolved around them. For his heresy, for daring to suggest a universe grander than the one sanctioned by doctrine, he was imprisoned, tortured, and ultimately burned at the stake. His tragic fate served as a chilling reminder that the cosmos holds its secrets tightly, and revealing them often comes at a great cost. The dream of other worlds lay dormant for centuries, awaiting the tools that could transform speculation into observation. That transformation began not with a triumphant discovery, but with a subtle, almost imperceptible dance. By the 20th century, astronomers theorized that a large planet, as it orbits its star, would exert a gravitational pull, a tiny tug on its massive parent. This gravitational handshake would cause the star to wobble. Imagine a powerfully built man walking an immensely strong, invisible dog. Even if you cannot see the dog, you can infer its presence by watching the man. You see him being pulled slightly off balance, first one way, then another, as the unseen animal strains at its leash. In this celestial analogy, the star is the man, and the exoplanet is the invisible dog. From our vantage point on Earth, we cannot see the planet directly, but we can observe the star's light with incredible precision. As the star wobbles toward us, its light waves are compressed, shifting toward the blue end of the spectrum. As it wobbles away, its light waves are stretched, shifting toward the red. This is the Doppler effect, the same phenomenon that changes the pitch of a passing siren. For decades, astronomers searched for this telltale stellar wobble, but the effect was so minuscule, so easily lost in the noise of a star's own activity, that success remained elusive. A different strategy was needed. Another method, elegant in its simplicity, relied not on a star's motion, but on its light. It is called the transit method. Picture yourself standing on a hill at night, watching a brilliant, distant lighthouse. Its beam is steady, a constant beacon in the darkness. Now, imagine a single, tiny moth flies directly between you and the lighthouse lamp. For a fleeting moment, the beam would dim by an infinitesimal amount. If you were patient and the moth's path was regular, you would see this subtle dimming happen again and again at precise intervals. In this grand cosmic theatre, the distant star is the lighthouse, and a planet passing in front of it is the moth. A space-based telescope, unhindered by the shimmering of Earth's atmosphere, could stare at tens of thousands of stars simultaneously, monitoring their brightness with inhuman patience. It would search for those periodic, almost imperceptible dips in starlight that signal the transit of a world across the face of its sun. The dream became reality in 1995. Two Swiss astronomers, Michel Mayor and Didier Queloz, announced a discovery that would forever alter our place in the universe. Using the wobble method, they had found a planet orbiting the star 51 Pegasi, but this was no Earth. It was a giant, a world half the mass of Jupiter, roasting in an orbit so tight that its year lasted only 4 days. This hot Jupiter defied all theories of planet formation. Our models, based on our own solar system, dictated that gas giants could only form in the cold outer regions of a solar system, far from their star's heat. Yet here was a behemoth practically skimming the surface of its sun. The discovery of 51 Pegasi b was not just the confirmation of a single new world, it was the demolition of our provincial view of the cosmos. It proved that other solar systems could be wildly different from our own, and it opened the floodgates. The hunt for exoplanets had truly begun. In the years that followed, our catalogue of known worlds exploded. We found small rocky planets, massive gas giants, and everything in between. And among this growing cosmic zoo, one particular class of planet emerged that was both tantalizingly familiar and deeply alien: the super-Earths. These are worlds more massive than Earth, but less massive than Neptune. Intriguingly, our own solar system contains no such planet. They represent the most common type of planet in the galaxy, and yet we have no local example to study. One of the most extreme and fascinating of these super-Earths orbits a sun-like star called 55 Cancri, a star visible to the naked eye, just 41 light-years away. The planet itself is designated 55 Cancri e. It is roughly 8 times the mass of Earth and twice its diameter. But its most astonishing feature is its orbit. It whips around its star in a breathtaking 18 hours. Its proximity is so extreme that its surface temperature is estimated to be over 2,000 degrees Celsius, hot enough to melt iron and vaporize rock. When first characterized, this world ignited a firestorm of speculation. Early models, based on its density and the composition of its host star, suggested it might be a carbon-rich world. Under the immense pressures and temperatures present on such a planet, this carbon could be compressed into its most stable, crystalline form. This led to a captivating, almost mythical moniker, the Diamond Planet. The press and the public alike were enchanted by the image. A world where mountains could be made of pure diamond, where glittering, crystalline landscapes stretched to the horizon, perhaps bathed in the eerie glow of lava rivers, carving paths through fields of graphite. It was a vision of unimaginable wealth and alien beauty, a treasure chest the size of a planet. But science is a relentless process of refining our understanding, and as we studied 55 Cancri e more closely, a harsher, more violent portrait began to emerge. The beautiful vision of a diamond planet gave way to the reality of a hell world. Tidally locked, one side of the planet is permanently seared by its star, a dayside locked in a perpetual, blistering noon. The other side is turned forever away, a night side locked in eternal, frigid darkness. The dayside is a cauldron. The star, 55 Cancri A, bombards the planet with radiation, thousands of times more intense than what Earth receives from the Sunday. This isn't just light and heat, it's a constant storm of high-energy particles, a stellar wind that acts like a cosmic sandblaster, relentlessly eroding anything in its path. Under this unending assault, a planet like 55 Cancri E should be utterly sterile of atmosphere. The process is a form of planetary destruction known as photoevaporation. To understand it, consider a simple pot of water placed on a powerful stove. The heat from the stove provides energy to the water molecules. They vibrate faster and faster until some gain enough energy to break free from the liquid surface and escape into the air as steam. This is evaporation. Now, scale that concept up to an astronomical level. The star is the impossibly powerful stove, a thermonuclear furnace of unimaginable intensity. The planet's atmosphere is the water in the pot. The star's X-ray and ultraviolet radiation slam into the upper atmosphere, heating the gas particles to extreme temperatures. These superheated atoms and molecules of hydrogen, helium, carbon, and oxygen are energized to incredible speeds, far beyond the planet's gravitational escape velocity. They are not gently evaporating, they are being violently boiled off into space. For a planet as close as 55 Cancri E, this atmospheric stripping should be ruthlessly efficient. Any primordial atmosphere, the hydrogen and helium gas it gathered when it first formed, would have been obliterated in a geological blink of an eye. Over billions of years, this process should have continued, peeling away layer after layer, leaving behind nothing but a dense, dead core. Astronomers even have a name for such a planetary husk, a Chthonian planet named after the Greek deities of the underworld. It is the scorched remnant of a gas giant that strayed too close to its star and was destroyed. 55 Cancri E was the perfect candidate. It was in the right place, it had the right mass. It should have been an airless, silent orb, a testament to the destructive power of a star. All our theories, all our models, pointed to the same conclusion, but the universe often has other plans. Studying the atmosphere of an exoplanet is one of the greatest technical challenges in modern science. It is an act of observation performed at the very limit of our capabilities. The light from the planet itself is completely overwhelmed, lost in the blinding glare of its host star. It is like trying to discern the color of a firefly's glow as it sits on the bulb of a searchlight, located in a different city. Directly seeing the atmosphere is impossible. Instead, scientists must rely on indirect methods, catching the faintest of chemical whispers, carried on the starlight itself. This requires a tool of unprecedented power and sensitivity, an instrument so advanced it can dissect a single beam of light from across trillions of miles of empty space. That tool is the James Webb Space Telescope. A monument to human ingenuity, its 18 hexagonal gold-coated mirrors form a single, giant eye nearly 7 meters across, the largest ever launched into space. Unfurled in the cold, silent dark, a million miles from Earth, shielded from the sun's glare, it is designed to capture the faint, ancient infrared light of the cosmos. It is humanity's great observatory, our eye on the origins of the universe, and our best hope for deciphering the secrets of worlds beyond our own. To probe the air of 55 Cancri E, astronomers used Webb to perform a technique called spectroscopy. The principle behind it is both simple and profound. Imagine you have a source of pure white light, containing all the colors of the rainbow. If you pass that light through a prism, it will split into a continuous spectrum. Now, place a clear glass jar filled with a specific, invisible gas between the light and the prism. When you look at the spectrum now, you will see something has changed. The smooth rainbow is interrupted by a series of thin, dark lines. The atoms and molecules in the gas have absorbed light at very specific colors, or wavelengths, leaving behind a unique barcode-like pattern of missing light. This absorption spectrum is a chemical fingerprint. Every element, every molecule, from hydrogen to water to carbon dioxide, absorbs light in its own distinctive pattern. By analyzing this fingerprint, we can determine the exact composition of the gas in the jar, even without ever touching it. In the case of 55 Cancri E, the star provides the pure white light. The planet's atmosphere is the gas in the jar. As the planet transits in front of its star, a tiny fraction of the starlight filters through this atmospheric halo on its way to Earth. The James Webb Space Telescope is the prism, its sensitive instruments designed to capture that light and spread it into a spectrum of incredible detail. The team of scientists pointed Webb at the 55 Cancri system, waiting patiently for the planet to begin its swift 8-hour journey across the face of its star. The expectation, based on all existing theory, was for a null result. The spectrum should have been flat, a clean, unbroken line of starlight, indicating that nothing stood between the star and the telescope. It would be the final confirmation that 55 Cancri was indeed a dead, airless rock. The data began to stream back from the telescope, a river of photons collected from across the void. In control rooms and university offices across the globe, scientists processed the information, their computer algorithms translating the raw data into a graph, a spectrum of light. There was a collective, palpable tension. This observation could close a chapter on this enigmatic world, but as the final spectrum resolved on their screens, it showed something else entirely. It was not a flat line. There, imprinted on the starlight, was a clear, unambiguous pattern of absorption lines, a chemical fingerprint. It was a signal that should not have existed. After billions of years of relentless stellar bombardment, 55 Cancri E was not naked. It was cloaked in a substantial atmosphere. The discovery was stunning. It sent shockwaves through the exoplanetary science community. The models were not just slightly off. They were fundamentally wrong. The chemical signature suggested an atmosphere rich in carbon-based molecules, perhaps carbon dioxide or carbon monoxide. This was not some tenuous, primordial envelope of hydrogen left over from the planet's birth. That would have been the first and easiest gas to be stripped away. This was a secondary atmosphere, a thick, heavy blanket of gas that must have been generated long after the planet formed. The central paradox was now sharper than ever. The star was undeniably trying to destroy the atmosphere. The evidence for that was overwhelming, and yet the atmosphere was undeniably there. This meant that some colossal planetary process must be fighting back, actively replenishing the atmosphere, pumping gases into the sky just as fast as the star could blast them away. The search for an answer turned our attention from the sky to the ground to the very heart of the planet itself. To comprehend the forces that could sustain an atmosphere in such a hellish environment, we must first look back at the history of our own world. 4.5 billion years ago, Earth was also an alien planet. It was a molten sphere, a global ocean of magma, shrouded in a primordial atmosphere of hydrogen and helium captured from the solar nebula. This initial atmosphere was quickly lost, stripped away by the young sun's intense radiation and powerful solar winds, in a process similar to what 55 Cancri is experiencing now. Early Earth was left a barren, hot rock, but it was not dead. Deep within its churning, molten interior, vast quantities of gases were dissolved in the magma like carbon dioxide trapped in a bottle of soda. As the planet's surface roiled with unimaginable geological activity, volcanoes erupted on a scale we can barely fathom today. These titanic eruptions were the planet's exhalations. They vented enormous volumes of gases from the mantle into the sky. Water vapor, carbon dioxide, nitrogen, and sulfur compounds. This process, known as outgassing, created Earth's second atmosphere. It was a toxic, suffocating veil, utterly alien to the blue skies we know today, but it was the crucial first step toward the world that would eventually harbor life. Now, transport this idea to 55 Cancri E and amplify it to a truly apocalyptic scale. On the planet's permanent dayside, the surface is not merely hot, it is so incandescent that the rock itself is perpetually molten. This isn't a world with scattered volcanoes. The entire surface is a single, planet-spanning volcano, a deep, churning global ocean of magma. Visualize this terrifying landscape. See the sluggish, brilliant orange waves of liquid rock, some 1,000 degrees hotter than any lava flow on Earth. Gases, superheated to thousands of degrees, bubble up from the depths, bursting on the surface in colossal plumes. A haze of vaporized silicates, a mist of molten rock, hangs in the lower atmosphere. From time to time, thin rafts of darker, cooler crust might crystallize on the surface, only to be torn apart and swallowed back into the incandescent sea. This is the engine that solves the great atmospheric mystery. The planet's interior, superheated by tidal forces and radioactive decay, is a massive reservoir of dissolved gases. This global magma ocean provides a direct and brutally efficient conduit for these gases to escape from the mantle and flood into the sky. 55 Cancri E is literally breathing. It is outgassing its interior on a planetary scale, constantly creating a new atmosphere from its own molten heart. This leads to a breathtaking concept, a state of dynamic equilibrium. It is a cosmic tug-of-war, a perfectly balanced battle between creation and destruction. High above the planet, the star's ferocious radiation is tearing the atmosphere apart, stripping away its upper layers and hurling them into the void. But from below, the roiling magma ocean is constantly replenishing it, releasing a torrent of fresh gas that rises to take its place. We can visualize this with a simple analogy. Imagine you are trying to fill a bucket that has a large hole near the bottom. The water leaking out of the hole represents the atmosphere being lost to space due to the star. The faucet pouring water into the top of the bucket represents the outgassing from the magma ocean. If you turn on the faucet so that the rate of water pouring in exactly matches the rate of water leaking out, something remarkable happens. The water level in the bucket remains constant. The bucket is never truly full, but it is never empty either. It is in a state of equilibrium. This is the life of the atmosphere on 55 Cancri E. It is not a static, ancient remnant. It is a dynamic, temporary feature constantly being destroyed and reborn in a cycle of unimaginable violence. The air on this world might be only a few million, or even a few thousand years old, a fleeting shroud that will exist only as long as the planet's internal heat engine continues to churn. The discovery of this process doesn't just solve the puzzle of one weird planet, it fundamentally alters our perspective on the nature of worlds throughout the galaxy. The revelation that a planet can actively generate and sustain an atmosphere, even in the most hostile corner of a solar system, has profound implications. It forces us to reconsider one of the most fundamental concepts in our search for life beyond Earth, the habitable zone. For decades, we have defined this region as the Goldilocks orbital band around a star, where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. Planets inside this zone were deemed our best candidates for finding life. Worlds outside it, like the scorching 55 Cancri E or the frozen planets of the outer solar system, were often dismissed as barren and uninteresting. But the magma ocean world proves that a planet is not a passive object simply at the mercy of its star. It is an active, geological entity. The presence of an atmosphere we now see may depend as much on a planet's internal geology as it does on its location. Consider a planet on the cold outer edge of its habitable zone. Traditional models might suggest its atmosphere would freeze and collapse onto the surface. But what if that planet has a powerful internal heat source, driving vigorous volcanism? This outgassing could pump greenhouse gases like carbon dioxide and methane into its atmosphere, creating a thermal blanket that keeps the surface warm enough for liquid water, far beyond where we thought it was possible. Conversely, the story of 55 Cancri E is a cautionary tale. It demonstrates that an atmosphere alone is not a guarantee of habitability. Here we have a world with a thick, substantial atmosphere, but it is a crushing, toxic inferno, utterly inhospitable to life, as we know it. This discovery refines our search, pushing us to look not just for planets of the right size, in the right orbit, but for worlds that show signs of a complex interplay between their surface, their interior, and their parent star. The era of simply cataloguing exoplanets is giving way to an era of characterizing them of trying to understand them as individual, multifaceted worlds, the James Webb Space Telescope is just the beginning. Future observatories, both on the ground and in space, are being designed with the express purpose of dissecting the light from these distant worlds with even greater precision. Missions like the European Space Agency's Ariel telescope will be dedicated solely to studying the atmospheres of 1,000 known exoplanets, providing a massive survey of the chemical diversity of worlds in our galactic neighborhood. We will search for the telltale biosignatures of oxygen, methane, and water, but we will also search for the geological signatures of carbon dioxide and sulfur dioxide, the signs of active breathing worlds like 55 Cancri E. The story of this impossible atmosphere serves as a powerful lesson in cosmic humility. It reminds us that our own solar system, with its orderly arrangement of small rocky worlds and distant gas giants, may not be the universal template. It might just be one quiet, relatively stable exception in a galaxy filled with systems more violent, more dynamic, and more bizarre than we ever dared to imagine. Every time we point our telescopes to the sky, we are confronted with the vastness of our own ignorance. The universe is not obligated to conform to our models or our expectations. It is a place of endless novelty, where magma oceans can breathe and worlds that should be dead can stubbornly cling to life. The shimmering, carbon-rich atmosphere of 55 Cancri E, maintained in a constant battle against its own sun, is a testament to the astonishing and unpredictable ingenuity of nature, and it is a beacon illuminating a path forward in our relentless, timeless human quest to understand our place among the stars